Chapter 9. Dot product and inner product. Section 1. Dot product. In this section, we will explore the dot product, a fundamental and essential operation in linear algebra. The dot product tells us how much two vectors are pointing in the same direction. It captures their directional similarity, or the strength of their alignment. The dot product is defined for two vectors of the same dimension, and the result is not a vector, but a single number, a scalar. For example, given two two-dimensional vectors, u and v, we can calculate the dot product in this way. As we can see, we multiply the corresponding components of each vector and then sum the results. The dot product is widely used in machine learning and data analysis. For instance, it forms the basis of calculating similarity between users and items, or evaluating the relationship and distance between data points. Now, let's take a closer look at the formal definition of the dot product. The dot product is defined for two n-dimensional vectors. Suppose we have two vectors, u and v, each with n components. We can write them as column vectors in this way. Then, the dot product is defined as the sum of the products of corresponding components. The dot product of two vectors, u and v, is represented by connecting u and v with a dot. What is important to remember here is that the result is a scalar, a single number, not a vector. It has magnitude, but no direction. This definition carries some intuitive meaning. For example, if two vectors point in the same direction, their dot product will be large. If they point in opposite directions, the dot product becomes negative. And if they are orthogonal, meaning they form a 90-degree angle, their dot product is 0. We will explore these geometric interpretations in more detail later. For now, please keep in mind that the dot product is essentially the sum of the products of corresponding components, and the result is always a scalar. Now, let's try calculating a dot product with a concrete example. We will use two-dimensional vectors to keep things simple and focus on the basic computation. Suppose we have two vectors, u and v. The dot product is calculated in this way. So, we simply multiply the corresponding components and then sum the results. The result is a scalar, a single number. In this example, we get 11, which suggests that the two vectors u and v are somewhat aligned in direction. Now, let's look at an example involving three-dimensional vectors. Even though we've added a dimension, the logic behind the dot product remains exactly the same. Let's consider the three-dimensional vectors u and v. The dot product is calculated in this way. Again, we multiply each pair of components and add the results. The result is a scalar, and in this case, it is 32. What is powerful about the dot product is that the calculation remains the same, no matter how many dimensions we are dealing with. So far, we've looked at how to define and compute the dot product. Now, let's turn to its geometric interpretation. What this operation actually tells us about the relationship between two vectors. The dot product can also be expressed using this formula. Here, double vertical bar u double vertical bar and a double vertical bar v double vertical bar are the length of the vectors, and theta is the angle between them. This equation tells us that the dot product is proportional to the product of the magnitudes of the two vectors and the cosine of the angle between them. If the vectors point in the same direction, cosine theta is close to 1, and the dot product becomes large and positive. If they point in opposite directions, cosine theta is minus 1, and the dot product is negative. And if the vectors are orthogonal, that is, at a 90-degree angle, then cosine theta equals 0, and the dot product is 0. The idea that orthogonal vectors have a dot product of 0 is very important. It shows up not only in linear algebra, but also in machine learning and statistics. For example, in principal component analysis, we project the data onto orthogonal axes to reduce dimensionality while preserving information. So, the dot product gives us a way to quantify the directional similarity between vectors. It is not just a computational tool, it has real geometric meaning. Now, let's look at how the dot product is actually used in real-world data analysis and machine learning. One of the most important applications is in measuring similarity between vectors. In many situations, we want to know how closely two vectors point in the same direction. For example, if we have a vector representing a user's preferences and another representing the features of a product, then if those vectors point in similar directions, we might predict that the user will like that product. In such cases, we use the dot product and a concept called cosine similarity. Cosine similarity is defined in this way. This formula normalizes the dot product by dividing it by the length of the two vectors, isolating the directional similarity. The value of cosine theta ranges from minus 1 to 1, where 1 means the vectors are perfectly aligned, 0 means they are orthogonal, and minus 1 means they point in exactly opposite directions. This approach is widely used in recommender systems and information retrieval. Whether it is a search engine ranking documents based on a query or Netflix recommending movies based on your watch history, the core idea often boils down to computing similarity between vectors using the dot product. So, as we can see, the dot product is not just a mathematical operation. It is a practical tool that connects directly to real-world applications and decision-making processes. Let's wrap up. The dot product is an operation defined for two vectors of the same dimension, and it produces a scalar, a single number. We compute it by multiplying the corresponding components of the vectors and summing the results. More than just a calculation, the dot product gives us insight into the directional relationship between vectors. One especially important case is when the dot product is 0. This tells us that the vectors are orthogonal or perpendicular to each other. This idea plays a key role not just in linear algebra, but also in fields like statistics and machine learning. The dot product is also used in cosine similarity, a popular method for measuring how similar two vectors are. This has practical applications in recommender systems, document retrieval, and more. So, the dot product is not only a tool for computation, it's a concept rich with geometric and practical meaning. Thank you for watching. Please thumbs up and subscribe to my channel.